At the edge of science, humans once dug the deepest hole in history, 12 kilometers into the Earth's crust. What they found shocked scientists and hinted at a hidden energy source beneath our feet. Today, that same heat may hold the key not only to endless clean energy, but also to unlocking one of the rarest and most valuable metals on Earth, lithium. This is the story of how geothermal power and lithium extraction might reshape the future of energy, technology, and even civilization itself. Chapter 1: The Depths of the Earth. Lessons from the Kola borehole. Imagine standing in the middle of nowhere, surrounded by frozen tundra. The air is still. The ground beneath your feet hides one of the strangest human experiments in history, a hole that goes deeper than any other hole ever dug. This place is called the Kola Superdeep Borehole in Russia. At first glance it looks unimpressive. A small, rusting metal cap covers what used to be a massive drilling project. But beneath that steel lid lies a story about curiosity, limits, and discovery. And this story matters today, because what scientists found in that hole may guide how we think about energy, technology, and the future of civilization. Digging to the unknown. The project began in the 1970s, during the Cold War. The Soviet Union wanted to push the boundaries of science. They asked a bold question: how deep can humans go into the Earth's crust? Over the next 2 decades, engineers drilled deeper and deeper, finally reaching 12 kilometers. That may not sound like much, but think about it. Commercial airplanes fly about 10 kilometers high. Flip that upside down, and imagine digging deeper than a jet's cruising altitude into solid rock. That's what they achieved. But the goal wasn't only depth. Scientists wanted to understand what the Earth looked like far below the surface. Every meter brought new data: temperatures, pressures, minerals, even signs of life. Surprising discoveries. What they found was shocking. First, the temperatures deep underground were far higher than expected. At 12 kilometers, it was over 180 degrees Celsius, so hot that drilling became nearly impossible. Then came another surprise: water. Not rainwater or surface water, but deep underground, trapped inside rock formations. Scientists had believed this was impossible at those depths. The discovery hinted that Earth's interior might hold far more mysteries than we imagined. There were also unusual minerals, strange crystalline structures, and signs that microscopic life could exist in extreme conditions. These findings challenged many ideas about geology and biology. Why it matters, you may ask. Why should we care about a hole in the ground, dug 40 years ago? The answer is simple. It showed us 2 things. First, the Earth is hotter, more complex, and more dynamic than we thought. Second, even with 20 years of effort, humans barely scratched the surface. Remember, Earth's crust is on average 35 kilometers thick. The Kola borehole went only a third of the way down. Below that lies the mantle, a zone of immense heat and energy we have never reached. This gap between our curiosity and our limits matters because right now, the world is searching for new sources of clean energy, and under our feet lies the largest source of energy on the planet: geothermal heat, the symbol of human curiosity. The Kola project eventually ended in the 1990s. Funding ran out. Equipment broke down. The heat was too intense for the tools of that time. Today, the site looks abandoned. The buildings are in ruins. The once grand drilling rig is gone. But the hole remains, sealed by a simple metal cap. It feels almost symbolic, a door to the unknown, locked and forgotten. Tourists sometimes visit, expecting a giant pit, but they only find a small circular cover on the ground. Yet beneath it lies the deepest human-made point on Earth. This contrasts the ordinary surface hiding. Something extraordinary creates a sense of mystery. It reminds us that the planet is full of hidden secrets waiting to be revealed. Lessons for today. The lesson of the Kola borehole is not failure, it's proof of possibility. In the 1970s, engineers managed to drill farther than anyone thought possible, with technology far less advanced than what we have today. Their discoveries warned us about the challenges: high heat, high pressure, strange geology, but they also opened our imagination. If we could reach just a little deeper, what else could we find? Today, new technologies like advanced lasers, plasma drilling, and enhanced geothermal systems are picking up where the Kola borehole left off. They aim not just to study the Earth, but to use its heat to power cities. The human drive to dig. There's something deeply human about digging into the unknown. We have always dug first for shelter, then for resources, then for knowledge. The Kola borehole represents that drive taken to the extreme. But this time, the reason to go deeper isn't just curiosity, it's survival. The world is moving away from fossil fuels. We need energy that is clean, reliable, and abundant. Geothermal could be that solution if we learn to reach it. Setting the stage. So why start with the story of the Kola Superdeep Borehole? Because it sets the tone for everything that follows. It's a reminder that the Earth's secrets are not easily given up, that even the most advanced nations struggle to reach into its depths. But it also shows that every meter down is a step closer to a different future, one where heat beneath our feet could power entire civilizations. The borehole is both a warning and an invitation. A warning about the difficulties ahead, an invitation to imagine what could happen if we succeed. The Kola borehole is no longer just a hole. It's a symbol of our restless search for knowledge, a reminder that the greatest treasures of the Earth are not always on the surface. And in the chapters ahead, we'll explore how that same curiosity has led to a new idea, combining geothermal energy with lithium extraction. It's a path that could transform not only how we power our world, but also how we build the devices, cars, and technologies of the future. Because deep down, the Earth is not just heat. It may also hold the rare metals we need to move forward. Chapter 2. Geothermal energy. The sleeping giant beneath us. When you stand on the surface of the Earth, it feels solid, calm, and unmoving. But just a few kilometers below your feet, the story changes. Down there, heat is constantly rising, created by the slow decay of radioactive elements and the leftover energy from the planet's birth. This heat is everywhere, flowing upward like an invisible tide. We usually don't notice it, but in certain places, it bursts through in dramatic ways. Volcanoes, geysers, and hot springs. This is geothermal energy. It's the oldest form of heat our planet has, and yet it remains one of the least used. Unlike wind or solar, it doesn't depend on the weather. Unlike coal or gas, it doesn't run out. It simply waits, deep beneath the ground, ready to be tapped. The basics of Earth's heat to understand geothermal energy. Think of the Earth as a giant heat engine. At its core, temperatures reach over 5,000 degrees Celsius hotter than the surface of the sun. That heat slowly leaks outward, moving through the mantle and into the crust. In some regions, like Iceland or California, the crust is thinner or fractured. This allows heat to rise closer to the surface, where we can reach it more easily. In those places, geothermal power plants have already been built. They drill wells into underground reservoirs of steam or hot water. The steam rises, turns turbines, and produces electricity. The process is simple, reliable, and clean. Once the water cools, it is injected back into the Earth to be retighted. It's a cycle that can continue for decades without major interruption. Geothermal in action. Let's take Iceland as the most famous example. The country sits on a volcanic hotspot where magma lies unusually close to the surface. Geothermal energy there isn't just a technology, it's a way of life. Around 90% of Iceland's homes are heated by geothermal systems, and a large share of its electricity comes from underground heat. California is another leader. The geysers, north of San Francisco, is the largest geothermal field in the world. For decades, it has generated clean power for hundreds of thousands of homes. And then there's Indonesia. Located on the Ring of Fire, it has enormous geothermal potential. In fact, experts believe Indonesia could one day be the world's largest producer of geothermal electricity. Already, it operates several major plants, and many more are under development. These examples show what's possible when the right geology meets the right technology. But they also reveal the problem. Geothermal energy today is mostly limited to places where nature does half the work. The advantages of geothermal. If we could unlock geothermal everywhere, the benefits would be extraordinary. Constant, unlike solar, which depends on sunlight, or wind, which depends on weather. Geothermal runs 24/7. It's not intermittent, it's stable. Renewable. The Earth will keep producing heat for billions of years. It's as close to infinite as energy gets. Low emissions. Geothermal plants release only tiny amounts of greenhouse gases compared to fossil fuels. In closed systems, emissions can be nearly zero. Small land use. Compared to massive solar farms or sprawling wind fields, a geothermal plant has a compact footprint. Local production. Unlike oil or gas, geothermal can be tapped right beneath a community, reducing dependence on imports. In short, geothermal looks like the perfect energy source. So why isn't it everywhere? The biggest challenge is location. Traditional geothermal plants need natural reservoirs, underground pockets of hot water and steam. Those are rare. That's why most geothermal today is clustered around volcanic zones or fault lines. Another barrier is depth. Heat is everywhere under the ground, but to reach it in most places, you need to drill several kilometers deeper than current technology allows, affordably. The deeper you go, the hotter it gets, but the harder it becomes to drill. At some point, equipment melts or breaks down. Cost is another factor. Drilling deep holes is expensive and risky. If you drill in the wrong place, you may not find usable heat, and the investment is wasted. This uncertainty has kept geothermal from expanding as fast as wind or solar. But here's where the story shifts from limitation to opportunity. Because in recent years, breakthroughs have begun to change the picture. Emerging breakthroughs, one of the most promising advances, is called enhanced geothermal systems, or EGS. Instead of relying on natural reservoirs, engineers create their own. They drill into hot, dry rock, then inject water under pressure. The water travels through fractures, absorbs heat, and comes back to the surface as steam. In other words, EGS makes geothermal possible in places where nature didn't provide the perfect conditions. Another exciting idea is closed-loop systems. Instead of injecting water into the ground and hoping it finds a path, closed-loop systems use sealed pipes filled with fluid. The fluid circulates, picking up heat directly from the rock and carrying it to the surface. Because the loop is closed, there's no risk of contamination, and it doesn't require a natural aquifer. These systems could turn geothermal into a universal energy source, not just one limited to special regions. Imagine being able to tap the Earth's heat beneath New York, Paris, or Tokyo, not just in Iceland or Indonesia. That's the promise of these new technologies. The sleeping giant. When we look at geothermal today, it's like seeing a giant asleep under our feet. We know it's there. We can hear it breathing in the form of geysers and hot springs, but most of the time, it lies quiet, untapped. Wind and solar have captured the spotlight in the clean energy revolution, and for good reason. They are cheap, scalable, and growing fast, but they are not constant. When the sun sets or the wind dies, we still need power. Geothermal, by contrast, is always on. It could be the backbone of a renewable energy system, steady, reliable, and abundant. If we can scale it up, it may solve one of the biggest problems in the energy transition: how to provide round-the-clock clean power. A hopeful future that challenges are real. Drilling deeper, handling high temperatures, and lowering costs will take time. But history shows that technology evolves quickly when the need is great. 40 years ago, drilling 12 kilometers into the earth seemed impossible. Yet the Kola borehole proved it could be done. Today, new startups are experimenting with plasma drilling, superhot EGS, and advanced materials that can withstand extreme conditions. Governments are investing. Scientists are collaborating. The momentum is building. It may take years, but the potential is enormous. Some experts say that just a fraction of the heat, stored, beneath the US alone could power the country for thousands of years. The same is true for many other regions of the world. Think of geothermal as a giant asleep, waiting for us to wake it up. It doesn't roar like a volcano or flash like a lightning storm. It waits, quietly, endlessly. If we learn how to reach it, geothermal could become the foundation of a clean energy future, steady where other renewables are variable, powerful where others are limited, and perhaps most inspiring, it's already here, beneath every step we take. In the next chapter, we'll connect this heat with another resource critical for our future: lithium, the white gold that powers electric cars, smartphones, and the batteries that keep renewable energy alive. Together, they may form a partnership that changes everything. Chapter 3. Lithium, the white gold of the energy transition. When people talk about the future of clean energy, one word often comes up: lithium. It has been called white gold, and for good reason. This soft, silvery metal is the backbone of modern batteries. Without it, electric cars would not run. Your smartphone would not last a day. Large-scale energy storage for renewable power grids would be nearly impossible. Lithium is not just another resource. It is the quiet engine behind the world's energy transition. Why lithium matters so much: think about your daily life. Almost every device you touch runs on some form of battery. Your phone, your laptop, your wireless earbuds, all powered by rechargeable lithium-ion cells. Now expand that picture to the global scale. Automakers are racing to electrify their fleets. Nations are building storage systems to stabilize wind and solar power. Each of these technologies needs lithium, and not just a little bit, a lot. The International Energy Agency predicts that demand for lithium could increase more than 40 times by 2040. That is not a distant future. It is within the lifetime of the devices you own today. As demand rises, so does the price. In just a few years, lithium prices have climbed to record highs. Companies compete fiercely for access, while governments worry about supply chains and national security. This tiny element has become the centerpiece of a global tug-of-war. The hidden costs of lithium mining. But lithium has a darker side. The way we currently extract it is far from clean. There are two main methods of getting lithium. One is hard rock mining. Often in Australia, huge amounts of ore are blasted from the earth, crushed, and processed. This requires massive amounts of energy and chemicals. The other method is brine extraction, common in South America's Lithium Triangle, an area spanning Chile, Argentina, and Bolivia. Here, salty underground water, rich in lithium, is pumped to the surface. The water is left to evaporate in giant ponds, leaving lithium behind. It sounds simple, but the impact is huge. Brine evaporation consumes vast amounts of water in regions that are already dry. Local communities often face shortages, while fragile desert ecosystems suffer. Mining also leaves chemical waste, alters landscapes, and threatens biodiversity. This is the paradox of lithium. The world sees it as the path to a clean energy future, but the way we obtain it is often anything but clean. It is a resource meant to solve climate change, yet it creates environmental damage of its own. A growing problem. These problems are not small or rare. They are becoming the rule, not the exception. Communities in South America have protested lithium projects, demanding accountability for water loss. Environmentalists warn that scaling up mining will destroy unique ecosystems. Even countries rich in lithium reserves worry about how far they should go. This leaves the world in a difficult position. On one hand, we urgently need lithium to cut our dependence on fossil fuels. On the other, expanding traditional mining could trigger new crises. So the big question becomes, is there another way? Lithium beneath our feet. This is where geothermal energy enters the story in a surprising way. Remember, geothermal reservoirs are essentially underground oceans of hot, mineral-rich water. These brines contain not only heat for producing electricity, but also valuable minerals including lithium. In fact, some geothermal fields, like those in California's Salton Sea region, are unusually rich in lithium. For decades, the heat was used to generate power, while the minerals were treated as waste. But today, with lithium demand skyrocketing, people are taking another look. What if we could tap geothermal energy and extract lithium at the same time? Two resources, one solution. Imagine this. You drill a geothermal well, pump up hot brine, and use it to produce electricity. Then, before sending the brine back underground, you pass it through filters or chemical systems that capture lithium. The water is then re-injected, leaving no waste ponds, no large mines, and no open scars on the landscape. This is not science fiction. Several companies are already testing these methods. Some use selective membranes. Others use adsorption materials that act like sponges, soaking up lithium ions. All of them share the same goal: turn geothermal brine into a dual resource, energy and minerals. The idea is elegant. One hole in the ground could give us two solutions: clean electricity and clean lithium. Why this matters for the future? If successful, Geothermal lithium extraction could rewrite the story of energy. It would reduce the need for destructive mining. It would strengthen the battery supply chain. It would even make geothermal power more profitable, helping this sleeping giant compete with other renewables. California's Salton Sea is already being called the Lithium Valley. Analysts believe it could supply enough lithium for millions of electric vehicles every year. And that's just one region. Other geothermal fields across the world might hold similar treasures. This approach could also reduce dependence on imports. Today, most lithium comes from a handful of countries. That creates risks: political, economic, and environmental. By tapping domestic geothermal resources, nations could build cleaner, more secure energy systems. The road ahead, of course, challenges remain. Extracting lithium from hot, corrosive brines is not easy. The chemistry is complex. Scaling up to industrial levels will take time and investment. Costs need to be competitive with conventional mining, but the direction is clear. More research, pilot plants, and government support are flowing into this field. The U.S. Department of Energy has already invested millions into geothermal lithium projects. Startups and established companies alike are racing to prove the concept. The dream is bold but simple: a clean battery metal, produced alongside clean power, from the same underground source. Closing thought: lithium is the white gold of our age. It powers our devices, our cars, and soon, perhaps even our cities. But if we continue mining it the old way, the price will be more than money. It will be ecosystems, water, and human well-being. Geothermal brines offer a way out of this paradox. They hold the promise of lithium without destruction, electricity without emissions, and a future where technology and nature can coexist. It is still early, the systems are still being tested, but the potential is enormous. The story of lithium is not finished, and the ground beneath us may hold the next chapter. Chapter 4: Lithium Valley. How the U.S. is betting on geothermal. The hidden valley, on the southern edge of California, near the Mexican border, lies a place that has long been overlooked. The Salton Sea is a vast, shimmering lake born from an accident more than a century ago, when engineers diverted the Colorado River and flooded this desert basin. For decades, it has been known mostly as an environmental disaster, a salty, shrinking body of water that left behind dying fish, toxic dust, and abandoned resorts. But beneath its surface lies something far more valuable than vacation dreams. In the hot brines deep underground, scientists believe there is enough lithium to power the world's clean energy future. This is why people now call the area Lithium Valley. Why here? The Salton Sea region is unusual for one reason: geothermal energy. For decades, power plants here have tapped underground reservoirs of scalding brine to produce electricity. There are already more than a dozen geothermal plants feeding clean power into California's grid. But that brine is not just hot water. It is also rich in dissolved minerals, especially lithium. For years, the lithium was treated as waste, a nuisance that clogged pipes and corroded machinery. Now, with global demand exploding, those same minerals look like buried treasure. Analysts estimate that the Salton Sea could yield tens of thousands of tons of lithium every year, enough to supply millions of electric vehicles, enough to make the U.S. one of the world's top producers. The pilot projects several companies are racing to prove it can be done. Controlled Thermal Resources (CTR) is building a facility that combines geothermal power with lithium extraction. Their Hell's Kitchen project is designed to generate clean electricity while pulling lithium directly from the brine before re-injecting it underground. If successful, it could supply U.S. automakers with a steady, domestic source of battery materials. Energy Source Minerals, another pioneer, has developed a process called Integrated Lithium Adsorption-Desorption (ILiAD). It uses advanced materials to selectively capture lithium ions, like a sponge soaking up only what you want. They've already run pilot tests and are scaling toward commercial production. Together, these companies are turning the Salton Sea into a living laboratory for the next generation of clean energy. The government's bet. Washington has noticed. The U.S. Department of Energy (DOE) has invested more than $2 million in research projects focused on lithium from brine technologies. National labs are working with private firms to perfect the chemistry and scale the systems. California state officials are also backing the effort, hoping to transform a struggling region into a global hub. The stakes are high. Right now, most of the world's lithium comes from Chile, Argentina, Bolivia, and Australia. Processing is dominated by China. That leaves the US dependent on fragile overseas supply chains. If Lithium Valley delivers, it could shift the balance. The US would have its own supply, mined, and processed domestically, without the destructive impacts of traditional extraction. The mystery angle, a modern Saudi Arabia. This leads to an almost science fiction question. Could this hidden valley make the US the Saudi Arabia of lithium? Think about it. In the 20th century, oil reshaped geopolitics. Nations that controlled petroleum supplies gained enormous power. Wars were fought over it. Economies rose and fell because of it. Now, in the 21st century, lithium may play a similar role. Batteries are becoming as critical to global infrastructure as oil wells once were. Whoever dominates lithium will dominate the energy transition. If California's Salton Sea really holds as much lithium as experts believe, then beneath this shrinking lake lies not just a resource, but a potential geopolitical weapon, a new kind of energy dominance, quiet, hidden, and waiting. Startups and innovation. The challenge is not just getting lithium out of brine, it's doing it efficiently, cheaply, and cleanly. Startups are experimenting with different extraction methods, selective membranes that let lithium ions pass through while blocking other minerals, adsorption materials coated with special compounds that grab lithium like Velcro, electrochemical systems that use electric fields to separate ions. Each approach has trade-offs: speed, cost, scalability. None are yet proven at massive industrial scale, but the momentum is real. Venture capital is flowing in. Automakers like General Motors and Ford are signing deals, eager to lock in future supplies. It is a modern-day gold rush, only this time. The prize is white and silvery, not yellow and shiny. Local challenges. Not everyone is cheering. The Salton Sea has long been an environmental tragedy. As the lake shrinks, toxic dust blows across nearby communities, raising health concerns. Residents worry that a new mining boom could bring more pollution or broken promises. Companies insist their methods will be different. Unlike traditional evaporation ponds or open-pit mines, lithium extraction from geothermal brine re-injects the water underground after processing. In theory, it leaves no scars on the surface. If done right, it could even fund restoration projects to help the ailing lake. Still, trust is fragile. Locals want guarantees, not just hype. The global ripple effect. If Lithium Valley succeeds, the impact will ripple far beyond California. For the US, it means energy independence, less reliance on imports, and a new industry creating jobs in a region that badly needs them. For automakers, it means stable, local supplies of a critical battery metal, more worrying about trade wars or shipping bottlenecks. For the world, it could reshape the map of resource power, shifting influence away from South America and China toward North America. Geopolitically, that would be seismic. Just as oil transformed the 20th century, lithium could redraw alliances and rivalries in the 21st. A valley of contradictions. There is a strange irony here. The Salton Sea was born of human error, a man-made flood that created an environmental mess. Now, that same place might hold a key to solving another human-made crisis: climate change. It is a valley of contradictions, where a dying lake might fuel a new beginning, where geothermal waste might power a clean future, where a forgotten corner of California could suddenly stand at the center of global energy politics. The idea of Lithium Valley is both bold and uncertain. The resources are there. The technology is emerging. The government and industry are aligned. But the leap from pilot projects to global supplier is still unproven. Will this hidden valley truly become the Saudi Arabia of lithium? Or will it remain another unrealized dream, a story of potential never fulfilled? For now, the world is watching. Beneath the cracked earth of the Salton Sea lies not just brine and heat, but the possibility of a new energy era, one that could redefine the future of nations. Chapter 5: A Dual Revolution. Energy plus Materials. Imagine a future where the power plants we build no longer just keep the lights on, but also supply the raw ingredients needed to build the very devices those lights shine upon. Imagine a world where energy and materials flow together safely, cleanly, and without tearing deep scars into our planet. That is the vision of geothermal energy's next great chapter. Not just heat, not just electricity, but electricity and essential metals like lithium, co-produced in a single system, a true dual revolution. From scarcity to abundance for over a century, humanity has treated energy and materials as two separate frontiers. Oil rigs provided fuel, and mines provided metals. We dug, drilled, and extracted, often leaving behind landscapes that looked like they belonged on another planet. Scarcity defined our approach. Every barrel, every ton, came at a cost. But geothermal offers a different path. It doesn't just give us heat, it gives us access to reservoirs that also carry dissolved minerals, including the so-called white gold of our time, lithium. If these resources can be tapped together, abundance replaces scarcity. Energy and materials become linked, arriving from the same source without the massive footprint of traditional mining or drilling. This idea is revolutionary, not because it changes what we need, but because it changes how we get it. Mining without mining. Think about the paradox of the clean energy era. We want electric cars, smart grids, and renewable storage. But to build them, we mine lithium, cobalt, nickel in ways that damage fragile ecosystems. In some parts of the world, mining means entire rivers poisoned, communities displaced, or massive carbon footprints just to deliver so-called green technology. The vision of geothermal lithium flips that paradox on its head. Picture this: a geothermal plant drilling into Earth's crust, bringing up superheated brine. That brine spins turbines to generate electricity. But before it is re-injected underground, it passes through filters and chemical processes that capture lithium. The brine then goes back into the earth, clean and intact. No open pit mines, no mountains leveled, no water reservoirs drained. Just energy plus materials, extracted together in what researchers are calling mining without mining. It sounds almost too good to be true. But in California's Salton Sea, and in other geothermal-rich regions, pilot projects are proving that this isn't science fiction, it's happening now. Philosophical reflection. How we dig this brings us to a deeper reflection. Throughout history, humanity has dug into the earth for survival. First for stone tools, then for coal, oil, and gas. These acts of digging powered civilization but left scars, visible scars on the surface, and invisible ones in the atmosphere. Now we are at a turning point. We are still digging, but for something different. Not for black smoke and carbon, but for clean heat and clean metals. We're asking, can we dig in ways that heal rather than harm? Geothermal lithium is symbolic. It suggests a new relationship with the planet. Instead of extraction that destroys, it offers extraction that replenishes, where the Earth's natural cycles are respected and even restored. This is not just technology, it is philosophy in action. Fueling the next era, the implications reach far beyond electricity and batteries. Imagine the ripple effects. Artificial intelligence gives AI requires massive data centers, which in turn demand reliable, clean power. Geothermal could provide it non-stop, unlike solar or wind. Pair that with lithium production, and you have the very batteries that keep AI systems stable. Electric vehicles, EVs, gives by 2030. The world may need over 5 times the current lithium supply, instead of importing it from faraway mines. Countries like the US could produce it domestically, tied directly to renewable power plants. Civilization's energy backbone gives geothermal lithium could help stabilize global supply chains. No more fragile dependence on a single region or market. Instead, a distributed network of geothermal factories, each producing both energy and materials, could become the new backbone of civilization. This is not just a technical innovation, it's a vision of resilience where cities, nations, and industries stand stronger because their foundations are cleaner and more secure. A turning point for humanity. If history is a story of energy revolutions, wood to coal, coal to oil, oil to renewables, then this may be the most profound leap yet. Not only changing how we power our lives, but how we build the tools that power our lives. Think about it. Instead of coal mines, we have geothermal wells. Instead of oil pipelines, we have lithium brine loops. Instead of smoke in the sky, we have steam that disappears harmlessly. For the first time, progress does not have to mean pollution. Growth does not have to mean harm. Civilization can advance without leaving a wound behind. That is what makes this a dual revolution. It's not just about energy. It's not just about materials. It's about redefining our relationship with the earth itself. So where does this leave us? Standing at the edge of possibility, geothermal lithium is not a guaranteed solution. It still faces technological hurdles, economic tests, and policy battles. But the potential is undeniable. Imagine the story we could tell in 50 years. How humanity turned a corner, stopped fighting with the earth, and started working with it. How we took heat and water from deep below and used it not just to survive, but to thrive, building cleaner cities, smarter systems, and a future where the earth remained whole. The Kola Superdeep Borehole once symbolized how far we could dig for knowledge. Today, geothermal lithium may symbolize how far we can go for hope. If you believe stories like this, where science, mystery, and hope collide, deserve to be told, consider subscribing to this channel. Share your thoughts in the comments. Do you think geothermal lithium could really transform the world? And if you found this vision as inspiring as I did, share this video with someone who cares about the future. Because the deeper we look, the more extraordinary truths we find.